Good morning, dear students. In this session, we are going to discuss about gas chromatography. In this, we will discuss about the advantages, principle of gas chromatography, instrumentation of gas chromatography, and applications. Introduction. Gas chromatography is a chromatographic technique that can be used to separate volatile organic compounds. In this, the mobile phase is a gas and the components are separated as vapors. Gas chromatography is quite similar to column chromatography, except that a gas is used as the mobile phase instead of liquid. Here we are using a gas as the mobile phase. It is a common type of chromatography used in analytical chemistry for separating and analyzing compounds that can be vaporized without decomposition. Let us see some advantages of gas chromatography. This technique, gas chromatography technique, has high resolution power compared to other methods. In this technique, even a complex mixture can be resolved into its components. The sensitivity of this method is quite high. That means very little amount of sample is enough for the analysis. And this technique gives good accuracy and precision. Next one, analysis of sample very quickly. That means within a minutes or even within a seconds can be done by using this gas chromatography. And one more important advantage is the cost of instrument is relatively low and its life is generally long. The technique is suitable for routine analysis because the operation of gas chromatograph related to calculations do not require highly skilled persons. Coming to the types of gas chromatography, we have two types here. One is gas solid chromatography, that is GSC, and another one is gas liquid chromatography, that is GLC. In gas solid chromatography, the stationary phase in this case is a solid. It is the affinity of solutes in gas solid chromatography, affinity of solutes towards adsorption onto a stationary phase takes place. Gas solid chromatography is based on the principle of selective adsorption. Principle of GSC is selective adsorption. Coming to the second one, that is a gas liquid chromatography. In this chromatography, the stationary phase is a liquid with very low volatility, while the mobile phase is a gas, that is a carrier gas. Usually some inert gases such as helium, nitrogen or argons are used. GLC is based on the principle of partition between the gas and the immobile liquid. Liquid phase. Gas liquid chromatography is the most widely used technique for separation of volatile components. Coming to the principle of gas chromatography. Components in the mixture are distributed between stationary and the mobile phase. Mobile phase means here a carrier gas that carries the mixture through the stationary phase. Compounds in the mobile phase interact with stationary phase as they pass through in the car. Due to the difference in the properties and structure of each component in the sample and the size and affinity of each interaction with the stationary phase are different. Therefore, under the same driving force, what we are applying in the gas chromatography, the retention time of different components differ in the column. Thus, moving out of the column in different orders. The samples or components are moving out with different orders. Coming to the instrumentation of gas chromatography. The instrument used to perform gas chromatography is called as chromatograph or aerograph, or it is also called as gas separator. It consists of the following components. One is a carrier gas which is filled in a cylinder, sample injection port, here sample injection port, columns, where you can see here the columns, thermostatically controlled oven, this is what thermostatically controlled oven, detectors, and the recorder system. Let us discuss one by one component here. First one is carrier gas. The cylinder or gas tank is fitted with a pressure controller to control the pressure of a gas. A molecular sieve to transfer filter dry gas and a flow regulator to ensure a constant rate of flow of mobile phase to the column. So, carrier gases which are used in these techniques are hydrogen, helium, nitrogen, and air. Hydrogen has low density and better thermal conductivity. However, it reacts with unsaturated compounds. So, and it is a inflammable and explosive in nature. Next one, nitrogen is inexpensive of course, but it gives reduced sensitivity. For that reason, we can't use. And coming to the helium, is the most preferred gas because of its excellent conductivity and inertness. For that reason, we are using a helium as a carrier gas in this gas chromatography. So that gas which is used in this technique should meet some of the following criteria. It should be chemically inert, should not react with any materials in the instrumentation, and it should be cheap and readily available. And the next, it should be high quality and not cause of any fire accidents, and it should give best possible results. And the next one, it should be suitable for the sample to be analyzed and for the detector also. Next one component, that is a sample injection port. The use of micro syringe, here we are using a micro syringe for injection of a sample. Syringe to inject a liquid or gaseous sample through a self-sealing silicone rubber diaphragm or a septum. See here, it's a septum into a flash vaporizer port located at the head of the column. In the figure, you can observe a septum and a syringe. And next, liquid samples are generally introduced by hypodermic microsyringe through a self-sealing rubber system into a small inlet chamber, which may be heated to cause flash evaporation. Here, the temperature must not be so high because that it may decompose the sample. So, solid sample must be dissolved in volatile liquids for introduction, or may be introduced directly if they can be liquefied. And gaseous samples may be introduced by use of a gas tight hypodermic needles of 0.5 to 10 ml capacity. This is about the sample injection port. Coming to the third point, important, that is the columns. These are of different size and shapes. That includes, the shape may include coiled or a bend or straight. They are mainly made of copper, stainless steel, aluminum, glass, nylon, and other synthetic plastics. The diameter of these columns is around 4.8 mm, and it can be of any length from few centimeter to over 100 meters. Length of the column is around few centimeters to over 100 meters. Support materials in which present in the column. Its main function is to provide mechanical support to the liquid phase, and it should have a large surface area and should be chemically inert, and it should get uniformly wet with the liquid phase and should be thermostable. These are some of the requirement of the support materials. And commonly used solid phases are glass beads, porous polymers, sand, etc. These are the support materials. Let us see types of columns. First one in this case is a packed column. These packed columns are fabricated from glass, stainless steel, copper, or other suitable materials. Stainless steel is the most widely used because it is most inert and easy to work with. Stainless steel. So, in gas solid chromatography, the columns are packed with size graded adsorbent or porous polymers. Coming to the gas liquid chromatography, the packing is prepared by coating the liquid phase over a size graded inert solid support. Coming to the open tubular or capillary columns. See, in this picture you can see porous layer open tubular column, packed capillary column, and wall coated open tubular column. In open tubular column or a capillary columns, the length of that column is around 10 to 100 meter, and the diameter, that is inner diameter, is usually around 0.1 to 0.5 millimeter. And these open tubular columns are made of copper, nylon, or glass. So there are mainly of two types in open tubular columns. One is wall coated open tubular, WCOT, and another one is support coated open tubular. This is called as SCOT. In WCOT, the inside wall of the capillary tubing is coated with a liquid phase in the form of a thin and uniform film. The carrier gas flow faces least resistance in this wall coated open tubular column because it is coated with a liquid phase in the form of a thin and uniform film. Coming to the support coated open tubular column, the inner wall of the capillary is lined with a thin layer of support material such as diatomaceous earth, onto which the stationary phase has been absorbed. It is also known as PLOT, porous layer open tubular column. SCOT is also known as porous layer open tubular column. SCOT columns are generally less efficient than WCOT, wall coated. Support coated is less efficient than wall coated columns, and both the types of capillary columns are more efficient than packed columns. So this is about the columns. Coming to the thermostatically controlled oven. Next point. Temperature maintenance in a column is highly essential for the efficient operation. It's very important. So column temperature is an important variable that must be controlled to a few tenths of degree for precise work. Thus, the column is ordinarily housed in a thermostated oven. It has to be placed in a thermostated oven. The optimum column temperature depends upon the boiling point of the sample and the degree of separation required. Roughly, temperature equal to or slightly above the average boiling point of a sample results in a reasonable elution time. It's around 2 to 30 minutes. For samples with broad boiling range, it is often desirable to employ temperature programming whereby the column temperature is increased either continuously or in steps as the separation proceeds. Coming to the detectors, the eluted solute particles along with the carrier gas exit at the end of the column and enter the detector. The detector then produces electrical signals proportional to the concentration of the components of the solute. This produces electrical signals. The signals are amplified and recorded as peaks at intervals on the chromatograph. So coming to the types of detectors, the most commonly used detectors are flame ionization detector and thermally conductivity detector. See, both these are sensitive to a wide range of components and both work over a wide range of concentration as well. While TCDs, thermal conductivity detectors, are essentially universal and can be used to detect any component other than carrier gas. FIDs are sensitive primarily to hydrocarbons only, whereas TCDs are universal and can be used to detect any component. Next, since thermal conductivity detector is non-destructive, it can be operated in series before a FID, that is a flame ionization detector, where it is a destructive one. Let us see these two detectors in detail. First one is flame ionization detector. In this detector, it implies a hydrogen flame near the exit of the column, and it is maintained in a small cylindrical jet made up of platinum or quartz. Effluent from the column with helium or nitrogen as a carrier gas are fed into the hydrogen flame, gets ignited and undergoes pyrolysis, produces ions. Formation of ions takes place here by the pyrolysis. And next, two electrodes are used to detect these ions. The formed ions are detected by using electrodes that provide some potential difference. The ions produced are repelled by the positive electrode, which hit the collector plate. The current produced in doing so is amplified and fed into an appropriate recorder. So that is about the flame ionization detector. Now coming to the thermal conductivity detector. This detector consists of an electrically heated source whose temperature at constant electric power depends on the thermal conductivity of the surrounding gas. It depends on the thermal conductivity of the surrounding gas. Operating principle, thermal conductivity detector, the operating principles relies on the thermal conductivity of the gaseous mixture. Here, helium or nitrogen serves as the carrier gas because of their relatively high thermal conductivity, which keep the filament cool and maintain uniform resistivity and electrical efficiency of that filament. The electrical resistance of this filament depends on the thermal conductivity of the gas. When analyte molecules elute from the column, the thermal conductivity decreases, and this causes a detector response. The response is due to the decreased thermal conductivity causing an increase in the filament temperature and resistivity resulting in voltage. Detector sensitivity is proportional to filament current when it is inversely proportional to the immediate environmental temperature of that detector as well as flow rate of the carrier gas. Similarly, few more detectors are there, that is catalytic combustion detector, which measures combustible hydrocarbons and hydrogen. Next one, discharge ionization detector, which uses a high voltage electric discharge to produce ions. Next one, dry electrolytic conductivity detector, which uses an air phase and high temperature to measure chlorinated compounds. Next one, electron capture detector, ECD, which uses a radioactive beta particle source to measure the degree of electron capture. ECD, electron capture detector, are used for the detection of molecules containing electronegative or withdrawing elements and functional group like halogen, carbonyl, nitriles, nitro groups and organomaterials. So this is about the instrumentation of gas chromatography. So now coming to the applications of gas chromatography. Qualitative analysis and quantitative analysis of liquids, gases and vapors, particularly of organic compounds, and to determine the percentage composition of the elements carbon, hydrogen, nitrogen, oxygen and sulfur in organic and organometallic compounds can be analyzed by making use of this gas chromatography. And this technique is used in detection of steroid drugs used by athletes in international sports competition. And it is also used in separation of fatty acids derived from fixed oils. Used in miscellaneous analysis of foods like carbohydrates, proteins, lipids, vitamins, steroids, drug and pesticides residues, trace elements, etc. Used in pollutants like formaldehyde, carbon monoxide, benzene, DDT, etc. can be monitored by GLC, gas liquid chromatography. And in analysis of dairy product, analysis by GLC for aldehydes and ketones, this technique is used. And it is used in the separation and identification of volatile materials, plastics, natural and synthetic polymers, paints and microbiological samples. It is also used in inorganic compound analysis and also used in residual solvent analysis. These are the important applications of gas chromatography. Now coming to the revision. In this session we have discussed gas chromatography. In that introduction, advantages of gas chromatography we have discussed, principles of gas chromatography, types of gas chromatography, that is GLC and GSC, and also we have discussed instrumentation of gas chromatography. And in that instrumentation we have discussed in detail about the detectors, thermal conductivity detector and flame ionization detectors. And in the last we have discussed about the applications of gas chromatography. And these are the references I have referred for this session. Thank you.